Welcome back. This is part 2 to the replacement for week 8. It's going over the packet that I sent out on the transverse wave in one dimension. Okay, so we just left off where we were talking about an oscillation. An oscillation means above and below some equilibrium, or side to side from some equilibrium. Okay, and this is, again, I marked this in green, and you're going to need this in calculus and both semesters, semester 2 of physics and physics 3, which is a thing that usually only physics majors take at MIT if you go to MIT. Okay, so I'm going to talk about Zara and Nick using the pulse wave, and I think, who did I talk about using? Jason and Glenn are the victims I picked for the oscillation. So Jason and Glenn, Jason is going to send this to Glenn in the oscillation, and Zara is going to send Nick a pulse wave. So you don't have to really keep those straight. All right, so the wave front, talked about this a little bit. Now remember, we're getting to this idea that phase has to do with where I am in this wave shape. This shape is a pulse wave shape right now. A is the wave front. If this were a pulse of light, it's not exactly how light would go, but if this pulse wave were Zara sending information to Nick, the fastest Nick would get any sort of information that something was coming to him, if his eyes were closed, right, and he's holding this green bead, is the speed with which A travels. So if this was light in a vacuum, it would travel with the speed of light, and that would be the fastest he could get any information. Notice that when the wave front first hits him, he doesn't get all the energy. The most energy is at the peak. It's at the peak here, and that's when he would get the most energy sent to him, or the first time he could get the most energy sent to him. All right, we won't talk so much about wave energy this week. We're going to talk more about wave energy next week, but wave energy is going to have some relationship to this wave shape as well. You can see that Zara could have higher amplitude, and what he would feel would be bigger. So that doesn't totally explain it, but there is going to be a relationship between the shape and size of this wave and the energy that Zara puts into it. All right, we talked about the wave front. All right, when we're talking about a wavelength, we talked about there was the Muggle answer, and there was something else that we wanted to talk about. So I said the Muggle answer, when we're talking about our definitions in class that we go over every single time, is that wavelength is the distance from peak to peak. This isn't quite lined up where it should be, but it should be from the tip-top point, from peak to peak, or trough to trough. And so that's the definition that most physics books, even high school physics books, will refer to it. But what we really are talking about is the distance from the same position in the wave. So they use peak to peak because those are positions you can easily find. When you look at a pulse wave, we don't have peak to peak. We just have one up, down. Oscillations are such a big deal, things that go back and forth, not pulse waves. Pulse waves are such an exception that we don't even talk about them really. Wavelength refers to an oscillation above and below the equilibrium line. For a pulse, we say it has a pulse width. We don't even talk about it having a wavelength usually. It's a pulse width. If Zara had a pulse maker that went both up and then one that she could do a down with, you could see that she could make a pulse wave up and then immediately follow it by a down one, an opposite and down one. And that would give you two pulse waves, one that's opposite, two pulse waves traveling down the beads towards Nick that had an up and a down. And if we look at a full wave cycle, which is what wavelength is, we would be here, we're ready to start a new wave. And with this peak and trough, we would be here ready to start a new wave. So I hope you can see that this would be what a full wavelength would be if we were talking about what a pulse wave is like. So the pulse width is measured from before you begin to when you're done, because this is the only part of the real pulse. But I hope you can see that it's half the wavelength if there was a down component to it. You're really not going to have to know that very much, except the only reason I'm talking so much about pulses is that it really seemed to be where the lights were turning on with the class. So that's why we're talking about pulses. Usually you won't have to talk about pulses until you get to electrical engineering. Okay, so let's get to the big idea, which is phase, angle, and phase, which is where am I in this wave? So here's our pulse kind of thing. And with the pulse, we have before I begin, the peak, and when I'm done. That's pretty simple. Look at point F. We have a different problem with point F in the oscillation. D is like, before I begin, all right, the beginning of my wave is here. This is my wave front. I go up to a peak. I come back to equilibrium, and then I'm going down. So I can't say, oh, if I'm back to equilibrium, if I'm on the equilibrium line, I know where I am in the wave. If I'm on the equilibrium line, I'm sorry, before or after here, if I'm on the equilibrium line, I could be about to go up or I could be about to go down. So whatever we use to describe the wave, it needs to be able to tell us where we are in the full wave, whether we're at F or D or here or here. It needs to be able to tell us where we are in this full wave. To do that, there's a math trick. On the math path, you will have 3 trigonometry homeworks or badges. I'm going to set them up as badges now. I have 3 trig badges. If you do all 3 trig badges, you will walk through all the ways that from starting with a triangle. If you've taken this class, the books leading up to this, we start with Thales and measuring something tall with a triangle. I suggest you review it, even if you remember doing that. And then in the calculus section, there will be something on just what is a function. But once you do the trig one, and if you've done all the calculus one, you will get to understand that we have these special things, sine theta and cosine theta, that we can use to draw a circle. These are special triangle pieces that we can use to draw circles. Theta has to do with the angle. If you look at the wave on a string in the oscillate, you see that there is this wheel. And once we start the wheel turns around. Now this is very much a real kind of mechanism that mechanical engineers use to turn turning motion into up-down motion. If you have motors are really easy to turn, as we'll see when you make your motor in the next unit. And then up-down, they have gears that make an up-down motion. But for those of us who've done the trig part, it's really good for us to remember we will be used to seeing this circle result in this beautiful sine or cosine wave. Okay. So you can select sine or cosine, and if you want to understand how this happens, how this comes to be, you'll have to do the math path and the 3 trig math path things. But even if you're not going to, I suggest that you take some time, and even if you're just going to follow along auditorily with me on this, open up the packet electronically, get this web address, and go play with this. Go play with this simulation. So you'll see that it's very similar to Wave on a String. It's called the Trig Tour. And go play with it and see that it will answer